All right, does anybody not have their slide back or? Sorry. Okay, so here's our exam stats. Hopefully you did as good as you hoped. The average was a little lower than last year's. Last year was 67. We're at 63, so it is what it is. So we're going to talk about it right quick, and then we're going to go ahead and start Chapter 8. I did post the Chapter 8 Mastering Chemistry. It's available for you to look at. Right now, I've got the due date set for the end of Thanksgiving week. We're only here a couple of days this week, or have lectures a couple of days. I don't think we'll make it through the entire chapter for that time, so that due date's probably going to get pushed back until after. So probably we'll come back and work probably on Tuesday following Thanksgiving, and then I'll set the due date on Wednesday after that, unless we just miraculously make it through. Exactly where we're going to be. So the exam wasn't impossible. Somebody did really good on it. The high was a 96. The low was lower than it needs to be. So with that, and we have the same chemistry. So the grade that you have posted on Blackboard, hopefully you read the emails that came out with that. That grade includes your bonus points that you have. At this point, you had 3 opportunities for bonus points. So those were 2 blood drives, the seminar speaker that we had on Thursday afternoon, and those of you that did come to see that guy, Dr. Du Bois, grew up in Boswell, Southeastern graduate. As a scientist, he's the real deal. I mean, he worked for a Nobel laureate at UT Southwest. He's a couple years younger than me in his career, but he's very established. He's already published 100 papers. His career, he can go anywhere in the world that he wants. We took him out to eat. Afterwards, he said that he typically flies out 3 to 4 times a month nationally at universities and conferences across the world. So he gets to travel the world and talk about the science. What he does in particular is the science of cholesterol, and understand his lab and the group that he worked with. Gold and Bernstein got the Nobel Prize for the invention of statin drugs, which are critically important in the control of cholesterol, and they help a lot of people improve their health and avoid future heart attacks. If not, now we're learning how to do it preventative to avoid the heart attack to start with. 25% of the American population takes statin drugs. Okay, the other opportunity that you have for bonus points is going to be this week, the canned food drive. So with the canned food drive, gives you bonus points that go towards clicker questions. Up to 10 cans, every can that you bring will give you a clicker point. So got some bad clicker days. This will offset that and give you that number of points. So you need to bring the cans of food down by my office to the department secretary. We have boxes down there. There's also a sign-in sheet. There's one for each class that I teach. So if you want to take advantage of that, up to 10 cans. We'll certainly take more than 10 cans if you have something you want to get rid of. But those, we're trying to distribute all that to the food banks so they'll be available for the Thanksgiving distribution, which is coming up in 2 weeks. So I need those by the end of the week. I want to participate in that. Well, I don't know. The ACS used to do it. I don't know if they are doing it this year or not. I gave them some boxes, and I do it as a class, and Dr. Wasman's class does it as well in organic. I don't know if any of the other classes do it or not. Typically, we get anywhere from 1,200 to 1,400 pounds. So, I don't know on campus if there are student organizations that are doing it, I hadn't seen it before I guess by email. So I don't know that that's happened this year or not. It used to be a lot of the sororities and fraternities would put together and do a drive, but for whatever reason, there hasn't been as much interest as was. Okay, so you know where you are in this. Let's just talk about the exam quickly and go forward. So, okay, it is what it is. I guess I want to see more points on the line to make sense to me. I would tell you if you're a person that's a lot of people aced all the mastering chemistry, so you're at 100%, but you didn't do near as good on the exam probably as you hoped. I tell you that try to work the problems more independently. Try to review them for the exam. In preparation for the exam, you can always go open those back up all you want to, but you've got to do something different in your exam preparation to be able to apply those to the test so you can move further up. That's odd to see that many points on the 100% that not are reflected when the exam scores. So we certainly need to come talk to me if you want to about what you can do to study differently. The thing that I encourage you to do the most is try to do all those problems on the old exams. Those suggested problems at the end of the chapters that I tell you that you ought to be able to take a look at, work those things out. If you're having a problem, don't understand what to do, come talk to the tutors, come talk to me. I want to try to get you to succeed at the level you want to succeed. So again, here's our exam. We're going to go over it quickly. Just some of the problems that we struggled with that I was surprised about was this first question. I mean, on the sheet study guide, I told you to know the 3 simple gas laws. Okay, Charles's law, Boyle's law, and Avogadro's law. 17 of 23 missed this problem. Okay, so Charles's law says that the volume of a gas is directly proportional to the temperature. I expected you to know those, so that's a legit question. Shouldn't have been that many of us missed that one. Number 2, a lot of us missed number 2. Says a mixture of 2 gases, so there's 8 moles of each gas are put in a container at STP. Which one of the following is true? So the correct answer you see is both gases have the same average kinetic energy. Let's talk about why the other ones are not true. It says the A is they both contribute equally to the density of the mixture under the conditions. To contribute equally to the density, they have to have the same molar masses. Gases have vastly different molar masses. So neon's here at 20, and xenon is much, much heavier at 131, so that's not going to be true. Both gases have the same molecular speed. Their speed's going to vary on their molar mass, so that's not true for B as well. And the mixture has a volume of 22.4 liters, and a lot of you chose that because you saw the term STP. That's true for 1 mole, but here we've got 16 moles that are there. So it need to be 16 times 22.4 to represent. So that one was one that tripped us up a lot. If you have a question about any of the other multiple choice, ask while I'm going through it. So number 5 says, which one of the following has the lowest pressures if they're all at the same temperature and in the same volume of containers? So the one that's going to have the lowest pressure is going to be the one that's going to have the highest molar mass because they all have the same kinetic energy. So what it means is the one that has the highest molar mass has the lowest velocity. All right. So this one, sorry, on this one we're looking at, they have the same volume. So I'm trying to work a different problem in my head. The thing that's going to vary on it's the number of moles. So there's 15 grams of each of the material. You're looking with the one with the fewest number of moles. The one that has the fewest moles is the one with the highest molar mass. So CO2 is 44, CO is 28, fluorine is 38, and the heavy guy was krypton's at almost 84. So that's the reason it was C. Number 7 says the gas is a gas at 35 degrees has a certain volume, 35 Celsius. What's the temperature if the volume is increased to 5 liters? So this is an example of what's the relationship between, which one of the laws tells us the relationship between volume and temperature? Is that Charles's law? Boyle's law? Yeah, that's Charles's law. And it says that the volume to temperature ratio is equal to the volume to the temperature ratio. So we want to solve this for T2. So T2 equals V2 times V1, or T1 divided by V1. The key to do it, though, is that you have to convert it from Celsius to Kelvin, and that's where almost all of you missed it at. So those of you that missed it, that's the common mistake that you didn't do. So when you take the numbers, 5 liters times 308 Kelvin divided by the 2.5 liters, it comes to 16 Kelvin. Subtract 273, get it back in Celsius, get a 343. Okay, number 9 was using Dalton's law of partial pressures. So you got this mixture of gases that are here, and I want to know, tell you the moles of each amount of gas, and then I tell you the total pressure. So the thing that you want to do is find out what's the pressure of the xenon. It's equal to the mole fraction of the xenon times the total pressure. So you find the mole fraction of xenon by the moles of xenon divided by the total number of moles. Comes out to 0.181. Multiply that times the pressure, and you get the 140 millimeters of mercury. We did good on 11 and 12. No, 10 and 11. 12 was one that more than half of us missed. Says, which of the following signs represent a system? And the system's doing work. Okay, so that means energy is flowing out of the system. All right, so, and then the heat is gained from the surroundings. So Q is going from the surroundings into the system. It's flowing in that direction. So if we look at that combination, it's C. So it's gaining heat from the surroundings, and it's expending energy. So the sign, or work, the sign for W is going to be negative. It's doing work on the surroundings. So C is the answer for that one. And we did an example just like that in our clicker questions, as well as did problems like that at the end of the chapter problem. 14 we actually did pretty good on. The only trick to 14 was realizing the one that wasn't given was the molecular compound. So the heat of formation for anything that's elemental state for the fluorine is 0. Did pretty good on 15. 17 kind of threw us for a loop. It says the specific heat of copper is given. I've got a mass of copper. It's initially at 25 degrees. It absorbs a certain amount of heat, and I want to know what is the final temperature. So when you set up the equation, the heat is equal to the mass times the specific heat times delta T. You rearrange it, solve for delta T. It says that delta T is equal to Q divided by M C sub S. I took kilojoules, converted it to joules, put in the mass, put in the specific heat, and it's 356 degrees Celsius. And most of you chose choice B, 356 degrees Celsius. That's delta T. That's not the final temperature. So the final temperature is equal to delta T plus the initial temperature. You add the 25 to it, it starts off at 380. Okay? So, I mean, its final temperature ends up at 381. The initial temperature was the 25. It added 356 degrees in temperature. Number 18 was another one that a lot of us missed. It says at constant pressure, the combustion of a certain mass of ethane, C2H6, give you a smaller mass, releases a certain amount of heat. Now I want to know what's the enthalpy of the reaction. So what I need to do is find the number of moles for the reaction. There were 20 grams divided by the molar mass. That gives me the moles of the ethylene. But there were 2 moles of ethylene per 1 mole of the reaction based on the stoichiometry. So that represents 0.33 moles of the reaction. So I take the energy released divided by the number of moles, and I get a minus 3120. That gives me choice B. We did good on those. Did very good on number 19 and number 20. So 20 was use Hess's law to rearrange and find the enthalpy of formation for our unknown. Most all of you got that it was a -2 times that. 22, quite a few of you missed number 22, but it wasn't more than 10. That's the looking at the color of radiation. So if we go through our spectra, Roy G. Biv. Okay, red, orange, yellow, green, blue, indigo, violet. I want to know which one has the lowest energy. So this end represents the shortest wavelength. Okay, but it also represents the highest frequency, and it represents the highest energy. So we wanted the one that had the lowest energy, so we wanted the color that was the most to the left. Okay, so we had first choice was orange as a color, purple's down by violet, green, and our other one was blue. Orange was the lowest energy color that we had in that. This was on a slide that I gave you. I talked about how we use X-rays and gamma rays to focus in on cancer cells, radiation treatment. Talked about people get a tattoo for alignment, and we hit the cells from the tumor from different directions to try to kill the radiation, because the radiation kills healthy and unhealthy cells, but by homing in from multiple directions, we can try to kill as much as the tumor as possible. But gamma rays and X-rays are the things that we do that with. We did good on the last two. Let's go to where we were pretty mixed at. So probably on this test more than others, there was more of a distribution of you either did well on the problems on the back, or you did well on the problems on the front, and not as many students did well on both, or good on both. Okay, so kind of tells you where you need to work on improving just to go forward. So the first one says 26. You've got a sample that's or syringe that's got some gas in it at a certain temperature and pressure. So you know volume, temperature, and pressure. The thing that's only left of the variables is the number of moles. So you can find the number of moles in the syringe. And it asks to what temperature does the syringe need to be heated or cooled in order to have a new volume, okay, and a new pressure. So some of you tried to solve this using the simple gas laws that related either volume to pressure or temperature to volume, but you got to take all the variables into account. To do that, you have to use the ideal gas law. So the number of moles are equal between the two. So you solve for the number of moles in conditions 1, apply that conditions to conditions 2. And some of you actually took the creative step of setting the two relationships equal to one another. And you said P1 V1 over T1 is equal to P2 V2 T2. And the R's actually cancel out. And that gave you another form of the gas law. But you solve that and you get the same answer as well. But if you solve it the first way, it's 0.01839 moles. Now you apply that to the second set of conditions where you've got the new pressure, the new volume, you know the number of moles, and it's got to heat it up to 721 Kelvin. See, I didn't say, yeah, I tell you temperature in Kelvin. So that's the temperature you need in. All right, 27, how many liters of hydrogen are needed to produce a certain mass of water at a temperature and pressure according to the reaction? So we're making this water, and we're making a certain mass of it. So this is just application to the reaction. We can take a known number of moles of this reagent and apply it back to the hydrogen gas, and I want to know the volume of the hydrogen gas. Okay, so I take the grams of the material I've got. I've got 110 grams. It weighs 18 grams per mole for water. It's 2 moles of water per 2 moles of hydrogen, so it's 2 to 2. So that comes out to 6.1 moles of hydrogen gas. Now I apply that to the conditions of the ideal gas law. PV equals nRT. Solve it for V. The volume equals to the number of moles times the gas constant R divided by the pressure. plug in the numbers, number of moles, the gas constant, temperature, and the pressure, and you need 149 liters of hydrogen gas. I think this is the one that when you did this, a lot of you truncated your values out on. Is it this one? No, it was this guy. So some of you wrote this out that it was 0.02 moles. Okay, so if I wrote something on it about carry significant three significant figures, if you rounded this off to this value, that's 1 sig fig, right? And we're trying to answer this to 3. Your answer could come up in the 600s, and some of you did. You did all the math right. You just didn't write it and carry any digits out. Never round to the end. Okay, the best thing to do is just carry all the digits out. But if you want to follow it, at least carry the number of significant figures plus 1 through all the calculations. But there were at least 5 or 6 of you that made this same mistake. You just rounded this thing off way too soon, and that caused a significant deviation in the answer you reported and what the true answer should have been. Okay, 28 we did pretty good on. I tell you, you've got an excess of this one reagent. That meant that the mass of the second reagent with the limiting one, so this is the limiting reagent, it's going to control how much energy is going to be evolved. So I take the mass of that material, divide by this molar mass, that gives you the moles. The grams cancel out. It releases a minus 1396 per 6 moles of the chlorine. So I set up the ratio minus 1396 per 6 moles. The moles of chlorine cancel out. It releases 238. Okay, there. 29 was kind of I think the most critical thinking problem that you had. So I gave you a certain mass of water at a certain temperature with a second mass of water at a certain temperature, and I want to know, you mix the two things together, what's going to be the final temperature? So the key to working this problem was the Q lost by one volume of water is equal to the Q gained by the other. So you set it up so that the mass times the specific heat times delta T is equal to negative of the mass 2 times the specific heat times delta T. And what happens is the specific heats cancel out, so that one should be there. So you've got the mass 1 times delta T, that's T final less the initial, times the negative of mass 2 times T final less T initial, and you solve for T final. So when several of you got to here correctly, and your math somehow got broke, so you didn't arrange the equation, distribute through. So first thing you do is distribute the T, or the 50 to both sides on the left, the negative 23 to both sides on the right. When you put that together, you get a final temperature of 36.3.
I did the...
It's just common to both sides of the equation. So if it would have been, anytime you put two of the same things together, like two pieces of iron, if they were put together to reach equilibrium, 2 samples of water, 2 samples of anything, if the specific heats are the same on each side, they're going to cancel out. Well, that's taken into account here. It's just that it's the exact same thing on both sides of the equation. So if you want to write in the number, that's fine. 4.184. It's still the same number. It's just common to both sides, so you can cancel it out. Same way that you can cancel out any variables on both sides of the equation. Okay. All right. 30 was calculate the wavelength of red light, and I want to know the energy associated with 1 joule. E equals the speed of light divided by the wavelength, the equation given off of the sheet. It was a plug and play. You just had to convert nanometers into meters. We worked a problem just like that in the end of the chapter problems. 2.67 times 10 to the minus 19 joules. And the last one was for hydrogen. I tell you, calculate the wavelength associated with a photon as it goes from the 4p orbital to the 2s orbital. So the key thing to realize is that's going from n equals 4 to n equals 2. and you apply the proper equation to it. So we've got an equation that says the inverse of the wavelength is equal to the constant. This is the Rydberg equation. Then we use the one with the smallest n first, the inverse of the smaller n, which is n2 squared, less the inverse of the second, which is 4 squared. That gives you this number, but that has units of inverse nanometers, or inverse meters. So to invert that, I simply go 1 over that number. That tells me the number of meters, 4.86 times 10 to the minus 7th meters. But I asked you for how many nanometers it was, so you convert from meters to nanometers by multiplying by 10 to the 9th. It's 486 nanometers associated with that wavelength. And the key's posted downstairs on the board. I'll post an electronic copy of it right underneath the exam, so you can go back and use this to review with as well. So if you want to put a copy off to study for the final. And just the only thing I'll say is just to some degree you're going to have to do this stuff again on the final exam. Yes.
When is our
During finals week.
dinner when?
It's not a standard time. Typically we do it on Wednesday. So because that's the closest class time that needs to win ours, so we do it at the same time as the class Wednesday, Monday, Wednesday, Friday. So that's our Monday, Wednesday, Friday at 11 o'clock. So that comes up to, honestly, I can't remember if it's Wednesday, the AM test, or the 11 o'clock.
Is there a study?
There is a study book for the final. I mentioned that at the start of the year. The ACS just got those in. I'll give you a one-page guide, much like what I gave you before, but they have a study guide, and there's actually a new one this year. I haven't even seen the new one, that it breaks it into chapters, things that you need to study for exam 1 versus Gen Chem 1 versus the Gen Chem 2 exam, first semester versus second semester. I think it's $25, but that could be used here. Use it in the spring as well. I would suggest it, yeah. So it's I hadn't even looked. I know the new one they said is a lot thicker, so it's got like twice the number of pages. But if you want one, you can ask any of the ACS members, or you can ask Dr. Paiva or the department secretary got as well. I think they just got me in last week. I know they did. But those are certainly, I would encourage you, if you're going to go forward in chemistry, you're trying to get as high as you can on the final as possible. I encourage you to get that. It kind of gives you some more examples. The way it does the study guide is just example problems at the example. And then there's key at the end. And it lets you look at more problems to work. I give you a lot of examples too, so it's certainly not required to buy. It's recommended. But it's $25. The thing I encourage you to do, if you got 2 or 3 people you study with, buy one and share it. Okay, so that's my suggestion. Any other questions about the test? Okay, so that is the end of Unit 3. We're going to proceed into the next chapter. So
We have one more test before the final.
we do have one more test. It will probably be on the Wednesday of the last week of class. It possibly will be on the Monday. We'll just have to see where we are on material. But it'll probably be one that we'll take in class, and I'll make it a little shorter. So it may be on the Tuesday. I just don't know where we're going to be.
How many chapters is it over?
It's over 3 as well.
3.
But these 2 chapters are a little shorter, 8 and 9 are the longer. Chapter 10, we only do about the first third of it. So 10 is a really abbreviated chapter first. So hopefully we're going to finish the material. We'll go through the bulk of chapter 8 this week, finish it up. When we get back from Thanksgiving, we'll go over chapters 9 and 10. The thing I'll tell you is that this is our last lab this week. So when we get back from Thanksgiving, instead of doing the lab, we'll spend it doing finishing the materials that we need to finish. That way we're not going to be rushed to finish material, and also gives us time to do reviews again. So this will be our 10th lab. This is the last lab that we did. Okay, any other questions? All right, so in chapter 8, the topic is is the periodic table and the organization, the properties of the elements, but we're going to talk a little bit about the development of the periodic table, a term called electron configuration. You've probably heard of that from your high school chemistry class. We're going to talk about where those numbers come from and how we apply it. In particular, we want to learn what the valence electrons are and how to write out the electron configuration for those, because it's the outer electrons that determine chemical properties. Talk about the quantum mechanical model that we introduced in the last chapter, how it applies to going forwards in chemistry. And then we have some trends that are important to understand about how the size of elements change as you go to different locations in the periodic table, and how the charge changes as well, and how this applies to both neutral elements versus ions, what happens to the electron configuration of ions, the magnetic properties, the radiuses, and something that becomes very important is the ionization energy. How much energy is required to put an electron on or take an electron off? The term that's associated with losing electrons is called electron affinity. And then finally, we want to apply this to why elements behave the way that we do. So something about the chemical behavior. Again, I strongly recommend that you take a look at these problems as well. If you go back and look at some of the problems that I gave you from the last exam, those are test questions. Okay, I'm pulling test questions out of these suggested problems. Okay, or one just like it, but I'll give you the problem verbatim. So those are a source of questions that I'm pulling them. All right, so why do we need to know things about the size of ions and the charges associated with them? One of the key things that we've studied as we've started to learn more about cell physiology is the transmission of nerve signals. And in particular, nerve signals are generated as potassium cations and sodium cations are pumped across membranes in a particular direction that causes a charged imbalance on one side of the membrane to the other. And that's what triggers things like the sensing of a nerve pulse. So I touch my finger, I feel it, that signal goes to my brain by repeating that reaction over and over and over through all the cells going through my body to reaching the nerves. It's also the similar mechanism that causes muscle reaction. So anytime you move a muscle, whether it's voluntary or involuntary, it's a similar mechanism where the ions are pumped in and out of these channels across cell membranes to create a potential difference. Okay, so if we look at things like the lithium ion or the lithium element, it has a size of 152 picometers. If we take the electron off of it, it gets a lot smaller. It becomes the lithium plus one cation. It shrinks down to 60. Something like sodium, the neutral element's 186 picometers, but the sodium cation is 80 or 95, a lot smaller. And just the difference between sodium and potassium, which are not that far apart. So the neutral element is 186 versus 227, but it's the cations, the 95 versus the 133. The difference in these two guys, somehow the cell senses this 30 or 40% difference, and it can tell which way that ion needs to travel across the membrane. Otherwise, we couldn't move a muscle in our body. We wouldn't have any sensation of detecting or feeling anything because we couldn't have nerve conductions. The size of ions, the charge of ions are critical to the properties of those elements in the periodic table. And the periodic table is organized in a way that allows prediction of the properties of an element simply by knowing what column or what role of an element is in the periodic table with relationship to its neighbors. So we want to understand some of the neighbor stuff. All right, so Mendeleev, we introduced him in the earlier in the semester. He's the person that came up with the periodic table as we have it today for the most part. He's a Russian chemist. He ordered the elements in terms of their mass, and when he saw repeating properties in the repeating patterns in their properties, he rearranged the elements so that they had increasing atomic mass, but the recurring properties were stacked underneath each other. So he put everything that had a similar property in the same column going up and down. So something like the halogens in the 7A family have similar properties going up and down that particular column of the periodic table. And he used this to discover elements that are predict elements that hadn't been discovered yet. I'll look at a couple of examples of those. But he put things in order based on properties rather than mass as an absolute order. So things like the iodide and the titanium, there's a switch in the mass. Iodide is the lighter element, and titanium weighs more in mass, but he recognized the properties need to be in the position where titanium was in front of iodine in order to conserve the properties of the halogen family of the 7-8. So he said it's the properties that matter more than the mass of the element. So here are a couple of his predictions that he made. So these are elements that hadn't been discovered at this time. Gallium is the first one. He called it Ica aluminum because it had a mass or a density very similar to what he thought aluminum would be. He predicted the atomic mass to be in the neighborhood of 68. It was slightly higher at 69.72. He said it would have a low melting point, and gallium is a unique metal. You can take this shiny, looks like a block of aluminum, and you put it in your hand, and because it melts at 28 Celsius, and what's body temperature? Celsius. Healthy body temperature. It's how much?
Higher than that.
It's higher than that. It's 37. So it just melts in your hand. I mean, it turns to a full, it looks like liquid mercury in your hand. It's a weird sensation to feel something, and when you touch it, it's solid as it can be. In a matter of seconds, it completely melts into a liquid. He predicted the density to be 5.9. He was dead on of that. He predicted the ratio with the oxide to be a 2-to-3 ratio with gallium oxide, and that's exactly what was observed. He predicted the ratio to form with the chloride to be a 1-to-3, and that's exactly what's observed. Another element he predicted, he called ectosilicon, which was named germanium. So he said it'd weigh about 72. He was very close on that one. He said its density would be around 5.5. He was off a few percent. He said the ratio would be 1-to-2 with oxygen. That's exactly what's observed. He said it would be 1-to-4 with chlorine, and that's exactly what's observed. So his predictions were pretty good, and he was chastised to some extent by even saying he left gaps in his periodic table. At that point, when people were organizing the periodic table, they based on what's been discovered. So he said, all right, there's a gap here for this element, and he just left a blank space in the periodic table for element 31. He said, y'all just haven't found it yet. And a lot of people thought, we've been doing this stuff for 100 years. We found everything there is to find. And he said, no, you haven't. So he stayed true with his belief, and it eventually proved to be true. So the why versus the what of things. Mendeleev's periodic law allows us to predict properties based on position in the table. Now, it doesn't explain the patterns of why there is this repetitive pattern. That's where the last chapter and the applications of where the electrons are, the quantum mechanical theory, come into play to answer the why portion of it. So we're going to bring that forwards into this chapter. So the why allows us to predict the what to some degree, and the two things together become very important because the periodic table is the most important tool a chemist will use. It's the thing that we look at constantly. Okay, so who organized the modern periodic table? If you missed this, okay, so yeah.
Does that prediction process work for the transition metals too? Like, does copper and silver have likewise properties?
They have properties that are predictive, but it depends on, because things like copper can oxidize to copper +1 or copper +2. Similar is true with silver, even though silver +1 cation is much more abundant than any other charge. The reason we call these the transition elements is because multiple things can occur. Where the ones that are on this side and this side, there's one common thing that occurs. Okay, so those are much more predictive. Okay, so everybody says Mendeleev. Actually, that's wrong. Okay, I haven't told you the why that's wrong. But that is the the correct answer that I'm looking for here. The final person that organized the periodic table, just to let you know the little white lie in it, is a person named Glenn Seaborg. And Seaborg was much later than Mendeleev. Seaborg was part of the Manhattan Project that discovered the atomic bomb, but they did a lot of the early chemistry and discovering the elements that are in this portion of the periodic table, the lanthanide and the actinide series. And at the early portion of when they were doing this chemistry in the late 1930s, early 1940s, the periodic table had these elements just stuck in the middle here, and it was stretched out a little bit. And Seaborg, after the conclusion of World War II, when he's finally getting to publish some of the things that he'd been working on for the past 10 years, he reorganized the periodic table into the current form we have today, plucked the lanthanide actinide series out, and made it a separate row down here below it. And one of his friends that was a famous chemist at the time said, "Don't do it. This will destroy your scientific reputation." And Seaborg said, "Well, the great thing about it is I have no scientific reputation because he's been hidden in secrecy of the government doing all of his career's work. He was complete unknown, but his organization of the periodic table got him the Nobel Prize 5 years later. But Seaborg is the last person to give us the modern periodic table. But Mendeleev is considered the father of the periodic table. Seaborg just passed away 6 or 7 years ago. I had the opportunity to meet him about 20 years ago. It's an amazing guy. Okay, so something that you've heard about in probably your high school chemistry is the term electron configuration. So electron configuration tells us the organizations of the electrons in their orbits around the nuclei of an atom. So quantum mechanics tells us something about the behavior of electrons, and it tells us that the electrons exist in only certain locations. We term these things locations orbitals. So when we give a description of where the orbitals are, the terminology that we use to describe this is called the electron configuration. If we look at hydrogen's one electron, so hydrogen has a atomic number of 1, so it's got 1 proton. To be electrically neutral, it's got 1 electron. The electron configuration term is 1s1. That's how we say this, 1s1. So the first 1 represents the principal quantum number. The s represents the orbital. And the second one, that's a superscript, represents the number of electrons in that 1s orbital. So let's view that just a little bit more. Now, where are the electrons going to be at? The Schrodinger equation tells us that hydrogen's 1 electron occupies the lowest energy possible. If we look up the Schrodinger equation or apply that to multiple electron systems, it doesn't give us an exact solution, so we can't solve it directly. But we can add additional terms for each electron that we add, and we have to take into account that the electrons, more than 1 electron being present, repels one another. And that's the problem, the failure of the Schrodinger equation, is it doesn't account for that. We can come up with approximate solutions to show the orbitals to be somewhat like hydrogen, but there are 2 concepts that we have to take into account that is not accounted for with Schrodinger's equation. And that's the things that affect the multiple electron systems. And that's that 1, electrons have spin. So we'll introduce this in the next chapter, but it's the simplest way to think about it is that you can think of a top that's spinning around. It could either be spinning one way or another way, clockwise or counterclockwise. The same principle applies to electrons. And the second is the splitting that occurs between the energy sublevels. So energy levels are exactly equivalent to one another. So let's look at the first of these, and that's the electron spin. So a group of scientists, Stern and Gerlach, did an experiment that showed that if you took a beam of silver atoms and they shot that beam of atoms into a magnetic field, that they separated the beam into 2 different directions. So what they proved is that the electrons spin on their axis. So here's what the experiment looked like. They had this beam of silver atoms that's shooting in here, and they run it into a strong magnetic field. and they find that some of the electrons bend up, or some of the atoms bend up, some of them bend down, some are attracted to the magnetic field, some are repulsed by the magnetic field, and they have a piece of photographic film here, or a collector, where they can see where they're striking at. So the why of it is because as electrons spin around, they generate a magnetic field, and that magnetic field will interact with another magnetic field. You've all played with magnets at some point in life, and if you take the opposite poles of a magnet, they repulse each other. No, if you put the same poles of a magnet, they repulse each other, north pole, north pole. If you put the opposite poles of a magnet, they stick together. Okay, so that's the same thing that's happening with the spin of these electrons. And if there's an even number of electrons, they split about 50-50. About half the atoms are going to have a net magnetic field pointing in the north alignment, and the other half are going to have the electrons pointing in the south alignment. So that becomes the north versus south splitting that appears to be about 50-50 with the silver atoms. Okay, so what happens is the electron spin is a fundamental property of all electrons, and they all have the same amount of spin. So if we want to think about these spinning tops, they're not spinning slow or fast. The only thing is they're spinning one direction or the other, and that's the only way that we characterize the spin of an electron. So we call this an up spin or a down spin, and we typically represent those with one of two different ways: an up arrow versus a down arrow, or we say it's a plus 1/2 versus a minus 1/2. Okay, why it's 1/2 versus plus or minus 1, and I don't know. So that's the reason, or the numbers behind it. So what happens is this electron spin becomes a fourth quantum number, or descriptor, that we have to tell where electrons are. And we call this the spin quantum number. And this is not one. The other three are predicted in the Schrodinger's equation. This one does not come out of Schrodinger's equation. So we give the spin quantum number the abbreviation m sub s. So that represents the electron spin. And it has simple values of either plus 1/2 or minus 1/2. It's the only values it can have. All the other quantum numbers depend on what's the quantum number above them, not m sub s. It's only plus or minus 1/2. So an orbital diagram is where we represent a square to represent each orbital, and then a half arrow represents the electron's spin in each one of those orbitals. So we'll put an orbital like the 2s orbital, which only has one shape, and then we'll put the electrons in with an arrow pointing up versus an arrow pointing down to represent the spins. Okay, so the key thing to understand about the electrons is when we put them in orbitals, they have to pair up. And the way they pair up is that you have one electron with an up spin, one electron with a down spin, and the spin pairs cancel out. So inside of orbitals, electrons must be paired. So whenever we have an orbital, we're going to have one electron that's going to be minus 1/2, one electron that's going to be plus 1/2, representing the up arrow and the down arrow. Now, if you've only got one electron in an orbital, does it matter if it's plus 1/2 or minus 1/2? And the answer is no. It just matters, is there one in there, or are they paired up? And the reason for that is the energy levels are the same between the two. So orbital diagrams are where we take this concept of taking a square, we represent how many electrons are present, and represent the electrons with an arrow. So the book shows the arrow as a half arrow. I typically do a traditional point on mine. That doesn't matter. Those two things are equivalent. The only thing that matters is the total number of electrons that you have in the orbit. And so if we look at the hydrogen and looked at its electron configuration, we said that was represented by 1s1. On the orbital diagram, we would represent the 1s orbital, and there's only one electron. So this represents the number of electrons in the 1s orbital. Okay, so that's the simplest system. That's a one electron system. Now we start to look at more than that. So where else do we put electrons? The Pauli exclusion principle says that no two electrons can have the same four principal quantum numbers. So whenever we look at these, and we have all these different quantum numbers, so we'll put these on the next page, but we've got the N, the L, the M sub L, and the M sub S. They have to be different at some point, and at minimum, they have to differ by what the M sub S's are. But you can't have two electrons that have the same four quantum numbers. Otherwise, they could be in the same space at the same time. And that's the reason we can't have the same four quantum numbers. They can vary by, have the same everything except for this last M sub S, but it takes two of them to fill up an orbital, and those two different ones represent the up arrow and the down arrow for any orbital. So they have opposite spins, they pair up. So what we need to know is what are the number of orbitals that are allowed at each sublevel, and that tells us the maximum number of electrons we can put in each sublevel. Now here we have to go back to the shapes that were predicted by the Schrodinger equation. So the S, we said, had one orbital associated with it. That was the spherical shape one. So if it's an S, so L equals to 1, or L equals to 0, that's the S sublevel. That means that only 2 electrons can go in that one. So whenever we have the S shape, it's one single orbital that can hold 2 electrons. If we go to the P shape, what happens with the P shape? Remember, the P's the ones that was the elongated figure 8, looks like an hourglass stretched out. There were 3 of those. So what happens with the P's is there are 3 different orbitals that coexist with the P's. So each one can have one arrow up and down. So that means a total of 6 electrons can be found in the P orbits, the P orbitals. If we look at what happens with the D's had 5 orbitals associated with those. So with the D's, you had 5 different D orbitals. So there are 10 electrons that can be placed in the D orbitals. And then finally, if you look at what happened with the F had, and it's where the balloon man went crazy and made all these different shapes. So there were 7 different orbitals that corresponds to a total of 14 electrons that can go in them. All right, so here's where the merging of the periodic tables come together. So we're looking for some organization of the periodic table that utilizes 2, 6, 10, and 14. Look at the periodic table a second and see if you can see those numbers repeated anywhere in the periodic table. You see anything that has a 2, a 6, or 10, or 14? Look at it this way. 2, 6, width of these periods, 10, count the elements over 14. That organization of the periodic table represents where these orbitals are. Okay, so when we look at the periodic table, we start to realize these two represent the s orbital. Okay, these ones, 3a through 8a, represent where electrons are in the p orbital. Okay, the ones in the middle represent the d orbitals, and the ones we plucked out down at the bottom are the f orbitals, the periodic table. Yes?
Are there more sublevels than that?
Sublevels? Nope. We've only got the 4 possible sublevels.
So that's 32 electrons, right? But there's more.
Okay, so we can put more electrons in, but now we go to the different periods. So this is where we start thinking about the layers of the onion. I'm going to write it so you can see it if we come back to it. So the key thing, and you said it, was the sublayers. So we got all the positive charge that's in the nucleus, however many protons are there. You've got an N equals 1 shell that has electrons in it. You have an N equals 2 shell that has electrons in it. And N equals 3. And N equals 4. And those become the layers of the onion. each one of those shells has different number of orbitals. So when you go to n equals 4, it can have F's, D's, P's, and S's. So it can have that many in that shell. Okay? You know what I'm saying? So you're just building to the different number of electrons by another shell that you put on it.
There's 32 electrons in one shell.
Maximum of 32. Okay? But only the biggest atoms have that. So when you start going to atoms that are in, here's the other, the different shells are represented by the period numbers in the periodic table. So period 1 represents the n equals 1 shell. Period 2, n equals 2 shell. Only the ones that are down here at the 5, 6, and 7 have 32. Have a full shell of 32. And the other ones are partially filled at that point. Okay? So we'll talk about how we lay all those out as we go forwards. Okay, so if we look at the allowed quantum numbers, these are the same things that we talked about in the last chapter. The only thing that we've done now is we've added one more. We've added these ones for the spin quantum number. So the principal quantum number could just be an integer value, and that tells us the distance from the nucleus. That's n equals 1, 2, 3, etc. The L tells us the shape of the orbital, and they are n 0 to n minus 1. Okay, so that tells us the shapes of the orbitals that we can have, and those translate into the S, P's, D's, or F's for the value. The M sub L represents the orientation in the orbit, and that's the M sub L. It goes from minus L to plus L. There's 2L plus 1 possible values that we can have for it. And then the last one is the direction of the electron spin, and it's either an up arrow or a down arrow or a minus or plus 1/2. There's only 2 possible orientations for that. So these are the 4 possible quantum numbers that we can have when we look at things. So now we did hydrogen. Let's look at helium. Helium's the next largest atom in the periodic table, atomic number 2. It has 2 electrons because it has 2 protons. Both electrons are in the first energy level. So that means they're both in the s orbit. Okay, so they're in the first s orbit. So it's called the 1s. And because they're in the same orbit, they have to have opposite spins associated with them. So helium's 2 electrons, by the electron configuration, we would say it's 1s2. And the way we would represent that in the orbital diagrams is the 1s orbit, and we'd have 1 electron in an up arrow, 1 electron represented with a down arrow. Okay, that represents both electrons. Now, these tell us similar information, the electron configuration and the orbital diagrams. They both tell us the total number of electrons there. They tell us where they're at. The additional information we get with the orbital diagram tells us the electrons are paired up or not. We'll see that as we go forwards. Now, if we wanted to assign the quantum numbers, we'd assign quantum numbers to each electron independently. So the first electron, represented by the up arrow in this one, its n number is 1. Its L number is 0. So where do these correspond to? This is an n of 1. This is an L of 0. That's S. There's 2 electrons in it, but the M sub L value can be a minus L to positive L, but if this is 0, that means that one has to be 0. And the first M sub S, the first electron, we say it's a plus 1/2, so that's the up arrow. The second electron has the same N value, L value, M sub L. The only difference is this is the down electron. Okay, so that's the down spin electron. So those are the 2 sets of quantum numbers that exist for both of the electrons that are in helium. Okay, that's at the lowest energy level. So now when we start to look at what are other possibilities that cause division and where the electrons are, we have to take into account the splitting that occurs in multiple electron systems. So the sublevels represent energy shells or sub-energy levels that exist within a primary energy level. So if we look at hydrogen, hydrogen's got 1 electron, so all those sublevels that exist have the same energy. And that's true if they're single electron systems. Whenever we have orbitals that are the same energy level, the terminology we use is degenerate to describe those. But what happens with multiple electron systems is that the sublevels become split. They have different energies. And the reason why is because of the charge-charge interactions that you have between electrons, and a term called shielding and penetration, which I'll explain in just a moment. What this yields, or the outcome of that, is that the different L values, the L quantum numbers, have different energies associated with them. So the one that has the lowest energy is the S, the P is a little bit higher energy, the D is a little higher energy, and F is higher energy than that. So those sublevels are now stacked. They're not degenerate. They have independent or unique energy levels associated with each of them, as long as it's a multiple electron system. All right, so we have to look at what happens when electrons get near each other. And electrons are alike charges. And whenever you have electrostatic interactions, the way that we calculate the energy associated with that is called Coulomb's law. And it says the energy is equal to this equation. And the key thing is that this term is just a constant. Okay, so it's got pi in it, and it's got the dielectric constant E naught in it. But Q1 becomes the charge of the particle 1. And typically we think of that being the charge of the nucleus, where the positive charge is. And Q2 represents the charge of an electron. Then the radius becomes how far is that from the nucleus to where that charge is. So now if we look at the magnitudes of these charges, if the charges are different, it's attractive forces. If the charges are similar, they become repelling forces. So alike charges, the potential is positive, and it decreases as the particles get further and further apart as the radius increases. But if they're if they're alike charges, like electron and electron, it becomes a positive. They're pulling. We want them to get further and further apart to minimize that. And if the charges are opposite, the potential energy is negative. They're attracting each other, and it becomes more negative as you get closer and closer together. So the things we looked at we can change, or that change the coulombic force, are the size of the charge. And what happens is the higher one of these charges gets, the stronger this interaction gets. So the interaction is directly proportional to the charge. So if we think about this in terms of the nuclei versus the electrons, what happens is electrons are attracted more strongly to a nucleus with a +2 charge than to a nucleus with a +1 charge. So you've got a nucleus with electrons spinning around it, and they're attracted to the charge. However much charge we have in this nucleus depends on something to the extent of how strong the interaction is. And so we've got 3 charges, we've got 2 electrons spinning around it. How much charge that electron sees is going to magnitude what's the strength of this force electrostatic, right, that's attracting this electron to it. Because that's ultimately going to determine, is the electron spinning around at this distance, or is it at this distance way out here, or is it somewhere in here close? Where are we going to find the electrons? Where's the most probable place to find the electrons? Okay, so here's where we have to take into account the concept of shielding and the nuclear charge. So whenever you have electrons in multiple electron systems, you have to take into account both the attractive force from the nucleus and the repulsive force that occurs from the other electrons that are present in the atom. So the repulsive forces cause the electron's charge to be reduced from the attraction in the nucleus. And the term that we use to describe that is called shielding. So I'm going to go back to my graph I had on this page. What happens is that this electron, if it looks and sees the nucleus, it sees a 3, this would be a -1 charge, and it sees this as 3+ charge. But if I have another electron running around out here at some further distance out, so let's say that I have an electron here at this orbit, when it looks inwards and sees, it sees this total charge being a combination So it sees a 3+ charge and then plus a -1 charge from the one electron. So the net charge it sees is a +2 because effectively this electron is shielding out one of those positive charges. And that's a term that we call shielding. So this electron doesn't experience a full 3+ charge. It's reduced charge with the nucleus. Or reduced interaction or attraction to the nucleus. Yes?
Is there a reason for why the electrons isn't attracted to the nucleus? Why does it orbit rather than?
Okay, so that's what we talked about in the last chapter. So that's what Niels Bohr came up with. And he said that the electrons are only allowed at certain predicted positions. And where they solved that with the Schrodinger equation is that basically, if you want to think about it, the electron can only drive on the road. Okay, that's the same way I'm going to simplify it as. The electron can be between here and here, or here and here, but anywhere in the middle is forbidden year-round. This place an electron can't be. You have to ask God that. Okay, so that's what the mathematics of quantum mechanics predict, and the why of it is from our understanding is this is what the equations predict. Okay, and it matches what we see with the physical properties. So why do matter exhibit very unique spectra? So if this weren't true, then all matter would exhibit a continuum of energies instead of having these very unique emission spectra associated with each element. And so they only have to be at certain allowed positions, otherwise we'd have a continuum for every element. And that's not what we see. So the why of it is that the electrons can only be in these allowed positions, and that's the only place they can be. Okay, so that's just what we know of it. And that's the way we have to understand. Why can't they be anywhere else? That's something we don't have a comprehension for right now. Okay, so now we have to take into the account that the shielding effect can occur, and what it does is it reduces the effective nuclear charge that the outer electrons see from the inner electrons. And the penetration effect is the fact that an electron closer to the nucleus sees a greater attraction than one that's further out. So if an electron can somehow is on the inner shells, it goes through the electron clouds of something else, it gets more attractive forces than one that's further out. So here's where we have to go back in the concept, are these electrons really floating around as discrete particles out here? Are these electrons really floating around as waves? And which one are they? They're both. That's where we're kind of stuck at. They're not one or the other, they're both. And once we start to think about it, it's a wave, and we talk about where they're at, and we can describe in terms of a probability of where we might find electrons in one place versus another. We have to consider that it can be in one place, but it can be to some degree in another place. So we look at where the electron's at by looking at where its radial distribution is, what that depended on, and how that relates to the maximum distance from the nucleus. So here's the concept of shielding as we think about it. So when we look at, go back to a better picture of what I showed you. Here's a nucleus that has +3. So that tells me it's a nucleus of lithium. It's got 3 positive charges. And if we look at the first 2 electrons, the first 2 electrons are in the n=1 shell. So they're spinning around here at this distance. So this third electron is further out. When it looks in for electrostatic interaction and attracts to the nucleus, what happens is that electron is shielded and has a weaker interaction with the nucleus because it also sees these 2 electrons that are in this n=1 shell. Okay, so it experiences a positive charge of about +1, not the full +3. But what happens if we look at the electrons that are closer in? So these electrons that are closer into the nucleus, what happens is they experience a full +3 charge because there's no electrons closer in than them to shield the nuclear charge in any way. So that's our concept of the shielding and penetration. Now if we start to apply that to where the electrons actually are as predicted by these radial distributions from the Schrodinger equation, what we see is that electrons that are in the 2s, so this is the 2s orbital, it can actually penetrate inside of the 1s to some degree, but certainly more so than the ones that are in the 2p orbital. Okay, so the 2p orbitals don't make it as close in to the nucleus as much. So what that means that the electrons that are in the 2s, they're closer to the nucleus and they have a greater attractive force because they're not shielded as effectively. Therefore, they're at a lower sublevel than what happens to the 2p electron. So now we have the idea that as these electrons can be at these different positions to get different levels of shielding, that not all the energy levels are degenerate for multiple electron systems. We have to say that the P is at a slightly different energy level than the S, which is a different energy level than the D and the F. So when we go to the things that are the N equals 4 and 5, the extent of the penetration becomes significant because what happens is that a lower S level lies at an energy level than the previous shell. So what that means is that when we get into the 4 and 5, this electron is actually a lower energy level than some of the electrons that's in the 3. Okay, it sneaks in at a lower level. We have to take those energy accumulations into effect. So here's the way that we take it in effect for multiple electron systems. So this is the energy level ordering that we have and the way that the electrons are going to stack into around any particular nucleus. The lowest energy level is the 1s. So that's where we're going to put the electrons first. And after we put our electrons in it, the electrons go to the 2s. After that, the next highest energy level is the 2p's, and there's 3 of those, then the 3s, then the 3p's. Okay, and now's where we get our first splitting that causes a major difference. Instead of going to the 3d's, the next lowest level is the 4s. So the electrons go into the 4s, then they go into the 3d's. Okay, now they go into the 4p's, and then they go into the 5s before they go into the 4d's. How do you remember this organization? So here's our organization, that kind of thing we want to do. This is called the diagonal rule. And what you do with the diagonal rule is you write out the possible organizations that you can have. So the S only has one S. Okay, N equals 1 can only be S. N equals 2 can be S and P's. N equals 3 can be S, P's, and D's. N equals 4 can be S, P's, D's, and F's. And the same as we go down. Everything else can have S through F. So now when you put the electrons in, you put the first electrons into the 1s. And you take your diagonal and you loop back up the top, and you go back at a diagonal again, and you go to the 2s. And then you loop back up to the top, and you go into the 2p and the 3s. So you just keep drawing diagonals through this. And then you come back to the top again, and the 3p and the 4s, and go into the top. And then you put them in the 3d, the 4p, the 5s, go back up the top again, 4d, 5p, 6s, go back to the top again. Then the electrons go into the 4f, the 5d, the 6p, and the 7s. This principle is called the off-ball principle. And when you really want to do fun at Christmas, you buy a t-shirt that has the off-ball principle on it. So if you want the ultimate ugly t-shirt contest, you can win by the time you explain that to your friends. Okay, have a good I'll post the lab for tomorrow, and I'll see you in pre-lab tomorrow.